All right, so we'll get started. Topic 5 is going to be mostly written notes for kind of the first part. I might have a PowerPoint later on. Topic 5 is focused on integration of equations. And we're going to look at the trapezoidal rule today, and then Simpson's rule in the next class, and then eventually the Romberg method. And if we had a graph or a line or a function, as we see here, this kind of line here, where we have f of x and x, when I'm integrating, what exactly am I doing? The area, right? So we're finding the area. So integration is finding the area. So if I'm going from 1 to 4, I'm basically looking at this area right here. So writing that down, integration is finding the area below the line. All right. So when we're looking at numerical methods, what we're trying to do is to approximate this area using different methods. So the first one we're going to look at is the trapezoid rule, right? But just to kind of mention here in words, so numerical methods are used to approximate the integral. And it could be of a function, right? So the integral of, f of x, or it could be also the integral of data points, right? So you could have, instead of a function f of x, I could just have data points and I want to integrate the points. Then numerical methods would be used, right? Because you don't have a function. All right, so then, and when we have experimental data without a model. So a function would be typically like it would be the model of a system, right? So if you don't have a model, then you just use the points as is. All right, so looking at the trapezoidal rule, first we're going to look at what is a trapezoid, right? So trapezoidal rule. So a trapezoid has the following shape. All right, where I have two sides. So this side is A, this side is B, and A and B would represent the length of each one of these sides. So this would be, A, and this would be my B. And then we have the height for the trapezoid, which is represented with H in this case. And the area for this trapezoid, all right, is A plus B divided by 2. So the average between A and B, A plus B divided by 2, multiplied by H. So that's the area. So now we're going to look at how to translate this to a graph like this one. All right. So as an example, I'll draw a line here. So we have a graph. And we're trying to go from, this point here, or to this point here. And what we're going to do is divide this into different segments. If I take one full segment, it would just basically be looking like this. And I would approximate the area as the area here, right? But I would have a lot of error in that approximation. So instead of using one segment, we're going to be using segments where we have step sizes of 1. All right, so I'm going to go from 1 to 2. Okay, let's say 2 is probably somewhere here. So 2 to 3 to 4. Just that there. All right, for the first segment, right, we're going to have, let's, I guess, use red here. We're going to have this. We draw a straight line from the y values. So this is f of x, this is x, and we approximate using a trapezoid shaped like this. All right? So the integral from 1 to 4 for f of x dx is equal to a1 plus b1 divided by 2 times h1. In this case, h1 is what we see here. Okay? And then a1 would be the height of the first point, right, on the y-axis. And then b1 would be the height on the y-axis. So this would be my b1. This would be my a1, but a1 is what? 0, right? So in this case, you know, in general, what we see here is f at 1 plus f at 2 divided by 2 times what? 1, which is calculated using 2 minus 1, right? The 2 points. The next segment, right, this segment here, we have a point, we draw a straight line, and then we're approximating using this area here. So this is going to be plus a2 plus b2 divided by 2 times h2. All right? So this is, in terms of the function, what is it? F at 2, right, divided by 2 times 3 minus 4. Sorry, 2. All right, and then we have one more segment, this last segment here. And this would be plus a3 plus b3 divided by 2 times h3. So this would be f at 3 plus f at 4 divided by 2 times 4 minus 3. So the general form for this equation, right, so in general, what we have is an integral, right, of f of x dx is equal to the summation for k equals 1 to n, and we have f of x k minus 1 plus f of x at k divided by 2 times xk minus xk minus 1, right? And this here would be considered delta xk. So in some cases, right, delta xk would not be constant. If I have a set of points and I don't have a function, it's just points, experimental points, they're not equally spaced, then I would use this general form here. Okay? And this form, so like I mentioned, is generally used for data. So mainly used for data. So now if we have delta xk as a constant, right, then we can simplify this equation by taking that constant out of the summation with the 2 that we see here. Just divide by 2. So let's write that down. So assuming equal intervals for the segments where delta xk is a constant, then the equation becomes integral from x naught to xn f of x dx equals delta xk divided by 2 times the summation. But in this case, there's a pattern that is noticed. If you look up here in this problem, how many times in here does f at 1 appear? Once, right? So we only see it here. F at 2 appears how many times? Twice, right here and here. And 3 is also twice. 4 is once. So because of that, what we're going to have is all the terms or all the points in between the first and last point are going to be multiplied by 2. Okay? But the other ones are only, the first and the last point is just appearing once, so we don't have to multiply it by anything. So in this form, we're going to write f at x naught, which is the first point, plus 2 times the summation of all the points in between the first and last point, which is going to be represented by k equals 1 to n minus 1. So this is going to be f of xk plus the last point, which is f of xn. Make sense? So there's also a third form, all right, for this equation, which uses the variables a and b as the starting and ending points. And then n would be the number of segments that we have. So we would be integrating from a to b, f of x dx, and we would write, in this case, b minus a divided by 2n, okay, because we took the whole segment. Instead of delta xk, the whole segment is b minus a divided by n. This here would be what? Same as this. Okay, so this would be our step size. B minus a divided by n would be our step size. And this is multiplied by f of x naught plus 2 summation I equals 1 to n minus 1 f of xi plus f of xn. I also could have written here, instead of x naught and xn, I could have written here a, I could have written here b. All right? But in general, this part right here, okay, is considered, you could say, the width. And then this part here is the average height. Right? So if I had like a graph like this, we have f of x, we have x, and we have some type of graph like this. So this here is a, and say this is b. So this would be the width, b minus a, and then, you know, the rest of it would be multiplied by the average height of this curve. That would give me the area, basically. Just another way of looking at this. So just to make sure you guys all understand, so A here is the starting point. B is ending point. And then N is the number of segments. All right. So now we're going to introduce the step size as H. All right. You guys seen it as H before, but we'll write it again. So let H be the step size. And this is important whenever we have many segments. Okay. If I tell you, solve the problem with 4 segments, then to find what's the second point, the third point, fourth point, and so on, you need this step size. Because you'll use A, and then from A, you do plus H. You got the first point. Plus H, second point, right? Right, so it's an easy way of finding these points for each segment. All right, so H is going to equal B minus A divided by the number of segments, N. All right, so this is an important equation. And this is essentially, right, the width of every segment. All right, it should be a V here. All right. So another kind of form for this equation up here, where we plug in H, right, which is instead of B minus A divided by N, we put H. All right, so we can write down that equation as well. So we can have integral from A to B, f of x, dx is equal to H divided by 2, and then we have f at A plus 2 times, right, all the terms in between, so I equals 1 to n minus 1, f of x I plus f at B. All right, so we derived basically the trapezoid equation using the kind of general, step-by-step method. Any questions?
This is the formula for any type of graph.
Yes. If you have equal segments. Okay, if you don't have equal segments, then you have to use this general form. Okay? You had a question? Or? No, okay. All right, so now we're going to look at kind of the general equations for the error for these equations. We're not going to use them too much in this course, but in some problems I will, like the example problem I'll do today, I will use it. So we're going to look at the error for single application. So whenever I say single application, it means I'm going, one segment. Okay. If I say multiple applications, that means multiple segments. All right. So single application of trapezoidal rule. The error in this case is approximated as ET equals -1/12 f second derivative psi times b minus a cubed. All right, where psi again is a value between a and b. For multiple segments or multiple applications, right, will be multiple segments essentially. Trapezoidal rule. Equation will be ET equals b minus a cubed divided by 12 and cubed times the summation of the second derivative for every segment. All right, so I equals 1 to n, second derivative xi I. And then we can also simplify this kind of term here by trying to find what is the average second derivative in kind of the segments that we are trying to solve. So again, looking at simplification of this, we're going to have an estimate for second derivative. All right, so sorry for the handwriting, but sometimes the pen just writes like that. All right, so summation of n I equals 1, f prime prime, xi I divided by n. So we took one of those n's in here and we moved it to here. Okay, so what we're doing is we're trying to find for that kind of summation divided by n, what's the average second derivative? And this is represented by this variable where it's equal to the integral from a to b times, or not times, but the integral of the second derivative at x dx divided by b minus a. All right. So in a way, you know, we're trying to find, when we're trying to find the average, we're basically trying to find the integral divided by the entire kind of segment. All right. So the equation above, this up here, ET, is approximated as EA, which is equal to, right, basically this first term with n instead of cubed squared times this average second derivative. So we're going to have minus b minus a cubed divided by 12 n squared times f prime prime average. All right. So we're going to be using this equation in the problem that we're going to do right now. So rectangular shape will have more error typically than this one.
Okay.
Especially if you have a very nonlinear. Okay. If I take taken the same segment as a rectangle, look at this.
Or it would require like.
Or you can go like that even.
Okay.
Then it'll overestimate. You can either overestimate or underestimate. So you'll have way more error. Actually, I forgot to mention here in this trapezoidal rule, the error is this area that we see here. All of this. Right? So this is the missed area. Which is basically the error in the trapezoidal rule method. Okay? But you could, so in the Simpson's rule, instead of using trapezoids, we basically kind of approximate an equation. Okay?
Similar to the equation.
We use the 3 points or 2 points to, or actually 3 points to approximate an equation. And using that, we estimate the area. So we'll see there are different methods. Trapezoid is not, you know, the most accurate, but it could be improved by, I'll show you in the next lecture, I think, or the one after, something called the Romberg method, and it will improve it substantially just by doing kind of 2 of these segments. Okay, you do 1 segment and then you do half or double the amount of segments basically, and you plug it into one equation and you just have a much more accurate estimate. Okay, so we'll see that later on in the other lectures. That's why we start off with this one simple, then we kind of get to the more complex. All right. So we still have half an hour, which is good. So let's do this example. So we need to use the trapezoidal rule to find the integral. All right, so example integral from 0 to 0.8 for the function 0.2 plus 25x minus 200x squared plus 675 x cubed minus 900 x to the 4 plus 400 x to the 5. That's the last term. All right, and this is dx. All right, using two segments. All right, so what's a in this case? So a is 0, and b is 0.8. What's h in this case?
And we have two, n is equal to 2, so it's 0.8 minus a over 2.
Right, so h is equal to b minus a divided by 2, so 0.8 minus 0 divided by 2 gives us 0.4. So that means, right, if I had the point system here, my first point is 0, my last point is 0.8, and the middle point would be what? A plus h, right? Which would be 0.4. Okay, if I had more segments, you can see how easily you can find the points in this kind of method. All right, so now we want to apply the equation. We know h, we know a, we know b. We can go back to this equation that we have up here. H divided by 2, f of a plus 2 times the midpoints plus f of b. In this case, how many middle points do we have?
1.
We just have one. All right, so in this case, we have a to b, f of x dx, right? F of x would be what? Would be all of this. This is f of x. So that's equal to h divided by 2 times f of x, or f of a, plus 2 times the summation n minus 1 from I equals 1 for f of xi plus f of b. So since we have n minus 1, this would be, the segments is 2, so 2 minus 1, we would only have one term in this summation. So we plug it in. H is 0.4 divided by 2. F at A is what? F at 0, right? And the value would be plugging in 0 to this equation up here, right? So if I plug in x equals 0, I get 0.2, right? This is 0.2. Plus 2 times f at a plus h, right? Which we said was 0.4. And if I plug in that to the equation, you know, we would get this is equal to 2.456 plus f at b, which is 0.8, and this here is 0.232. You do the math, you get a value of 1.0688. So this is what estimated area or integral, basically. All right. Second part of this problem, which I didn't write here, is to solve or estimate the error. All right, so we're going to estimate the error. Estimate the error. So we're going to apply the equation that we saw up here, this equation here. All right. So we have EA is equal to negative B minus A divided by 12n squared. This is cubed and the average. So we plug in the average, right, which was the integral of A to B f prime prime x dx divided by B minus A. In this specific case, right, we have the function. So I can easily integrate its second derivative to what? The first derivative, right? So this is basically equal to, again, B minus A cubed divided by 12n squared times f at B prime minus f prime at A divided by B minus A, right? And you know, the function f of x is, you know, we wrote before 0.2 plus 25x minus 200x squared and so on. So f prime would be 25, right, minus 400x and so on. Okay. So you basically plug in the values to this equation. So b is 0.8, a is 0. You cube that, you divide by 12 times n. N is what? 2, right? We have 2 segments. Multiplied by f at b, which is f at f prime at 0.8. If you do the math, you would get negative 23 minus 25 divided by 0.8 minus 0. Right? You do the math, you find that this is 0.64. So the true value, when I'm looking at this EA here, this estimated error, right? This is the estimated kind of true error. So if I look at the equation, EA is equal to the true value minus the estimate. So that means the true value is equal to EA plus the estimate, or estimate plus EA, right? So then in this given equation, I can say, all right, my true value is equal to 0.64 plus the estimate that we got up here, which is 1.0688, right? Which gives us 1.7088. The true integral in this case, okay, true integral, in fact, is 1.64053. Okay, so you can see we kind of, using this approximated error, we got closer to that true value. Again, it's not, you know, perfect, but it's an approximate. So I have a practice problem, which you can do at home, I guess, or if you want, we have 20 minutes. You could try it here as well. So practice problem. I want you to find the integral from 0 to 5 for the function 2x squared minus x plus 5, okay, using 2 segments. And once you've done that, also estimate the error using this equation that we just also used. right? So you should get, integral equals 106.25. EA is going to equal negative 10.417. And then for the kind of estimated true value, you should get 95.83. All right. Any questions? So do you guys want to do this now or?
Double derivative, we
Yeah.
can replace it with the one that we did before, which
Yeah,
is
yeah.
first derivative, this one, right?
Yes.
This is only for two segments. Derivative.
This problem?
I
No.
mean, the derivative, first derivative is only for two segments.
Which one?
Let me go up. This one.
No, this is n would be the number of segments. So,
Okay.
so you can have as many. And you can see that as I increase the number of segments, the error becomes smaller and smaller. Right? Because you're dividing by n squared. So if I have 5 segments, then I'm dividing by 5 squared.